This chart visualizes a historical assumption in economic development. The x-axis represents income per capita, and the y-axis tracks environmental degradation. For decades, the consensus was that these two variables moved together in a straight upward-sloping line. More industry meant more wealth, which required perpetual ecological destruction. In the mid-20th century, economist Simon Kuznets identified a different pattern regarding wealth. He demonstrated that as a society develops, income inequality initially rises, but eventually falls, forming an inverted U-shape as institutions and education mature. Environmental economists later adapted this inequality framework to address pollution and resource extraction. They proposed the environmental Kuznets curve, or EKC. The hypothesis argues that environmental damage is not a permanent state of affairs. Instead, the severe pollution associated with early industrialization is a temporary phase of development. This forces a choice between viewing the curve as an objective law of economics or an optimistic anthropocentric narrative that assumes human progress solves all problems. The EKC's upward trajectory is the scale effect, where early development relies on heavy resource extraction. At the turning point, this relationship flips. The downward slope is driven by technological and structural effects, shifting the economy toward cleaner energy and services. This reflects the modernist belief that human societies can eventually grow out of environmental damage through economic maturation. To prove if this theory reflects reality, economists must translate the narrative into a statistically testable econometric model. To test the EKC, we must observe a region undergoing rapid structural change. Consider Bali, Indonesia, which balances tourism, agriculture, and urbanization. If we only test the EKC using time series data, looking at all of Bali as a single unit over time, we lack comparative variance. This makes the model vulnerable to spurious regression, where trends appear connected but are statistically meaningless. Conversely, if we use cross-sectional data, comparing Bali's distinct regencies at one single moment, we fail to capture dynamic changes as wealth increases year over year. The solution is panel data. By combining cross-sectional and time series dimensions, we can track 9 distinct regencies in Bali over a 7-year period. This creates a matrix of 63 total observations. This multiplication of data points provides the necessary statistical power to track the relationship between wealth and pollution across both time and varied geographies simultaneously. This core econometric equation tests the EKC. Y is the environmental indicator, X is income. A linear regression cannot map a U-shape, so researchers introduce a quadratic variable, income squared. To prove the curve exists, beta 1 must be positive, representing initial environmental damage. Beta 2 must be negative, proving growth eventually reduces pollution. Finally, taking the first derivative, negative beta 1 divided by 2 times beta 2, calculates the exact income level where pollution peaks. However, there is an empirical reality check. If the math calculates a turning point of $80,000, but the region has only reached $40,000, the phase shift hasn't actually occurred. The curve remains incomplete. Even with panel data, we have to account for unobserved regional heterogeneity. A tourist hub generates waste differently than an agricultural zone, even if their per capita incomes match. Econometricians use 3 main models to handle these differences: the common effect model, the fixed effect model, and the random effect model. The Chow test checks if the regional differences are significant enough to abandon the baseline common effect model. The Hausman test determines whether those specific regional traits correlate with our independent variables, deciding whether the fixed or random effect model is appropriate. In EKC studies, the fixed effect model is usually the most critical. By isolating unique fixed geographic traits, like local culture or topography, it prevents those localized factors from falsely skewing the relationship between income and pollution. While the econometric math is highly rigorous, the existence of the EKC in the real world is sensitive to the type of environmental indicator being tested. Look at this graph tracking local pollutants. Dataset A plots along the theoretical curve because the mechanism is localized. Citizens experience direct health impacts and demand regulatory intervention. But with global problems like carbon emissions, dataset B breaks through the turning point, accelerating continuously. The curve collapses because global pollutants lack immediate, localized consequences. Without direct harm to the local population, the institutional and public pressure required to trigger that downward slope does not materialize. This brings us to a central critique of the EKC framework within modern environmental studies: the illusion of outsourcing pollution. A wealthy nation can maintain high domestic consumption while showing a drop in domestic emissions. On paper, it looks like a perfect curve. The underlying reality is that the wealthy nation hasn't necessarily developed cleaner technology. It has simply offshored its highly polluting manufacturing sectors to developing nations. This creates a disconnect between national accounting and global reality. A single nation's panel data might show a U-curve, but net global environmental degradation is only being relocated. The environmental Kuznets curve is an effective econometric tool for tracking developmental phases, but the data proves that economic progress does not automatically guarantee ecological sustainability without deliberate global policy intervention.